Welcome back to our discussion on kinematics. Right now we're talking about vorticity. And we are pounding our way through relative vorticity. We went through a discussion of vorticity in natural coordinates, and we said that in natural coordinates we can look at two terms, the curvature and the shear of the wind. And now we're going to look at it in terms of Cartesian coordinates. And to do that, we need a little bit of math. Vorticity is defined as the cross product between the del operator and the wind, the three-dimensional wind. You know, wind is three-dimensional. In thunderstorms, of course, you have really strong updrafts. That's in the Z component. We call that the W component of the wind. But also there's the east and east-west, north-south components of the wind, which are U and V. So we have to account for those also. So we're going to take the three-dimensional cross product, or the three-dimensional del operator, which is the change in the x direction, the change in the y direction, and change in the z direction. And we are going to do the cross product with the three-dimensional wind, which has u, v, and w components. So this is what it looks like. You set up a matrix. You remember The Matrix? It was a great movie. Well, that's the wrong matrix. This is mathematics. So we've got the I, J, and K unit vectors. We've got the derivative in the x direction, the derivative in the y direction, and the derivative in the z direction. You guys all had calculus, so you know this. And then u, v, and w, which are the components of the wind. So this is three-dimensional vorticity. And what it gives you the spin in 3 dimensions, meaning that it'll give you the horizontal spin, and also it'll give you the vertical spin in the zx plane and the zy plane. So that's kind of complex. Usually we're not too concerned with the zy and the zx, the vertical vorticities. We're more interested in the vorticity that's on a horizontal plane, the xy, looking at weather maps. The z, y, and the zx, the ones that are tilted, are important for thunderstorm formation. But we're going to just look at the vorticity that we see on a weather map, which is on the xy plane. So for synoptic scale motions, xy is very important. For thunderstorms, the other ones are more important. And also fronts, the other ones are more important. So to get rid of those two vertically tilted vorticities, we are going to do the dot product with the k unit vector. And that will eliminate the two horizontal or the two vertical components of vorticity. When we do that, this is what we get. Our horizontal vorticity, which is zeta, is equal to the change in the v component of the wind in the x direction minus the change in the u component of the wind in the y direction. So we're going to look at this a little bit more closely. We'll take the first term, how the v changes in the x direction. And remember, the v is the north-south wind, the component of the wind. We're going to look at how that changes in the x direction. So this is what we've got. We've got some spinning here, some vorticity field. This is the wind field, a vector field. Looks like the winds are getting stronger as you go out from the center. They're kind of weaker, closer towards the center of the spin. And we're going to look at how the wind changes, the v component of the wind, the north-south component of the wind, as you move away from the center out in the positive x direction towards the right. And looking at the spin, we can tell right away, if we draw our s and n coordinates, we know that this is positive spin, positive vorticity, because our n coordinate points towards the center after we draw our s. So we know that's positive. So looking at this, as we move away from the center towards the x direction, we see that the wind is getting stronger from the south to the north. The arrows represent the strength, which means that it looks like it's getting stronger as you move out towards the positive x direction. So the change in v, the component of the wind that's moving to the north, is getting bigger as we move in the x direction. So that's the component, the north-south component. If I draw those components, it looks like they're getting bigger as I move in the positive x direction. So that means our change in v in the x direction is positive vorticity. And that makes sense because we said that using natural coordinates, the spin is positive. So that's okay. We're good there. Let's try the second term, which is the change in u in the y direction. U is the east-west component of the wind, and how's that change as you move towards the north? So let's see. Here we've got that spin again. And as we move to the north, moving out from the center and moving up along the y-axis, we see that the wind is getting stronger again, but it's becoming more negative. It's not pointing in the positive x direction, it's pointing in the negative x direction, the wind. So as we move to the north, we can see that it's becoming more negative. In other words, the change in u is negative as we move in the y direction. So this term is negative. And we know that the vorticity is positive. We did that with our natural coordinates. So to make this positive, we'll throw a minus sign out front, and that makes this equation happy. So that is vorticity in Cartesian coordinates. In meteorology, we use Cartesian coordinates a lot, but natural coordinates help us visualize what's going on. I hope you enjoyed that.